All right, welcome in. It is Thursday, February 4th. Thanks for being on this morning for Math 8. We are going to continue today with equations. We started a new topic on Tuesday. We are looking at equations, how to make them, what they mean, all kinds of that stuff. So we're going to continue with that today. We are on lesson 3-2 in the textbook. So again, I highly recommend that you guys follow along in the textbook and get those, fill in those pages as we go, because all these problems that are in the computerized version are exactly the same as what is in the textbook, in your printout workbook page that you guys can write on. So anyways, let's go ahead and do that. I'm going to present here and we'll get started with the video.
What page?
Great question. I would have to. I think my book is downstairs. I'll go. You want me to run down and grab it? It's probably like page. I'm just gonna take a guess. It's probably page 120 or somewhere around there. But I can go find it. I left my book downstairs, so let me go check it out. I was way off. We're in the hundreds. It is 171. 171 is the page. Yesterday's pages were 165 through 170. So we are on page 171 today. Lesson 3-2. Okay, now that I'm back, let's roll this thing. I should have rolled this thing while I was gone. My bad. Sorry for wasting 30 seconds of everyone's life. Let's roll.
What are different representations of a function? Think about this question during the lesson. A 10,000-gallon swimming pool needs to be emptied. 2,000 gallons have already been pumped out of the pool and into the tanker. You can tell from the diagram that the pump moves 720 gallons of water per hour. How can you determine how long it will take to pump all of the water into the tanker? How can you use what you know about linear equations to solve the problem?
All right, so linear equations are what we talked about last lesson, which are those, or last unit, which are those y equals mx plus b, right? So we talked about that as the slope and the y-intercept, right? The slope is what's attached to the x. That's the slope is the m, so it's attached to x, mx, and then the plus b is the plus whatever. That's the starting point, right? So in this particular case, in this particular problem, we have a linear function, so to speak, because we have a unit rate, which is going to be our slope, and we also have a starting point because it tells us how many gallons we have already pumped, right? So does that make sense? It says we've already pumped 2,000 gallons. So if we were going to write this like a linear equation, 2,000 gallons is going to be your y-intercept because that's our starting point. We've already pumped 2,000 gallons. So starting right now, we're going to have an equation that says y equals blah, blah, blah plus 2,000, right? Because 2,000 is our starting point. Our unit rate is 720 gallons per hour. And we know that it's a unit rate because it has the word per in it. And we've talked about that. Per means divide. whenever you have a unit rate, you have something per something. In this case, it's gallons per hour. That's how fast the pump works, right? So our linear equation for this line or for this model could really be written as y equals 720x plus 2000, right? And I'll put that up here on the Jamboard so you guys can see what I'm talking about here. If we are writing a linear equation, y equals mx plus b, right? We know that m is the slope because it's attached to the x. We know that b is the y-intercept, which is also known as the starting point, right? So our starting point is 2,000 because it says we've already pumped 2,000 gallons, right? And our slope would be our unit rate. So 720 gallons per hour with an X on it, right? We could write this information as an equation just like that, where X would represent the time in hours, right? And Y would represent the number of gallons pumped, right? If we put in 2 hours, we would get 1440 plus 2,000, which would mean 3,440 gallons. So we still would not be there because the problem said we need to pump 10,000 gallons out, right? But now you've seen kind of what I'm talking about here. We're relating last unit's prior learning to this unit's new topic, okay? This can be written as a linear equation or a linear function.
One way is to draw a diagram that represents the situation, then write an equation. The top bar represents the total amount of water to be pumped from the pool, 10,000 gallons. The first bottom bar represents the amount of water already pumped, the initial value, or y-intercept, 2,000 gallons. Each additional box represents the amount of water pumped per hour, the constant rate of change, or slope, 720 gallons per hour. We need to determine H, the number of hours needed to pump the remaining water. Which change, or slope, 720 gallons per hour. We need to determine
Pause.
H, the number of hours needed to pump the remaining water. Which equation does the diagram represent?
All right, I was trying to pause it and it wasn't.
Select
cooperating.
your answer.
720 gallons per hour.
Okay, so I want to go back to something they just said because it's important and it's a review, but it's important. The amount of water pumped every hour is a constant rate of change, which is the slope, right? All those things we learned last unit that all of those words mean the same thing. The constant rate, the rate of change, the slope, the unit rate, all of those things are the same value. They're different ways of saying the same thing. So we know that our rate, which was 720 gallons per hour, is going to be the slope of our line. And we did that, right? When we went to the Jamboard, our slope was 720 gallons per hour. We could have written it like 720 divided by 1, right? Because it's gallons per hour. But we don't need to put the divided by 1 because that's self-explanatory, right? Anything divided by 1 is itself. So if you see a whole number, and we talked about this when we were graphing lines, if you see a whole number, you know that you can assume that that means over 1, right? So you're going to go up 720 spaces and over 1 on the graph, right? Anytime you see a whole number, you know that you're going to go right 1 space. All right. So I just wanted to go back and reiterate that. If you hear the word constant rate or unit rate or rate of change, you know that that's going to be your slope, right? And we know that 720 gallons per hour should tip you off right away that that's a unit rate. Something per something, right? We talked about unit rates a lot earlier in the year and in 7th grade. Sorry, I forgot to change the tab back. But here you go. All right, so let's continue. And let's pick the equation.
We need to determine H, the number of hours needed to pump the remaining water. Which equation does the diagram represent?
All right,
Select
So-
your answer.
we look at this. Which one of these looks like what we wrote? Now, I didn't put in the 10,000, and I used X because that's what we're used to. Y equals mx plus b. But we have y equals mx plus b in this equation. We have a format that's similar. Let's look back at our Jamboard and see what we got, right? They put in the 10,000 because that's how we're going to end up solving this problem. So they put in the 10,000 here. That's the total number of gallons we need to pump to finish the job. But this is what we got. 10,000 equals 720x plus 2,000, because 720 is our unit rate, gallons per hour. 2,000 is where we started. It said we'd already pumped 2,000, and we need to get to 10,000. So we would need to, what we're going to need to do is isolate the variable and solve for x. But let's look back and see which one of these looks like us. Again, it's 10,000 equals 720x plus 2,000. Looks like this one, right? They used the letter H to represent hours. I used the letter X because that's what we typically use in linear equations, but it doesn't really matter what letter you use, right? Any letter can represent anything. They used H because we're trying to find the number of hours, so they used H. But this one right here is going to be our equation.
You can now solve this equation to find.
All right, so they're going to do all this math. I'm going to do this a lot slower because they do it super quick, okay? So I'm going to show you how we do this and go over how to solve. And I'll use the H this time because they use H. So we're solving this equation. We need to find out what H is. I'm going to circle that in a different color. I'll circle it in yellow. We need to find out what H is. So how do we do that? We need to isolate the variable. Isolate means we need to get H all alone, all by itself, right? That's what isolation is. So the first thing we need to do is get rid of this 2,000. We have a plus 2,000, so we're going to subtract 2,000 to get rid of it, right? Because plus 2,000 minus 2,000 is 0, so it's gone. Now, we always have to do the same thing to both sides, right? Whatever I do over here, I have to do to the other side to make all things equal because we have an equal sign. So since I subtracted from the right side 2,000, I'm going to subtract 2,000 from the left side. Well, 10,000 minus 2,000 is 8,000, obviously. 10 minus 2 is 8. Now we have 720H equals 8,000. We still need to find what H is. We need to get H all alone, right? So our last step here is we have 720 and H next to each other with no sign, right? So if something is next to each other with no sign, we know that that is times, right? We are multiplying 720 times H. Well, again, we always want to do the opposite, right? This was a plus 2,000, so to get rid of it, I subtracted 2,000. This is times 720. So I'm going to divide by 720 to get rid of it, right? And we know that if we have something on top and bottom, we can cancel them out, right? 720 divided by 720 is 1. So these, in essence, disappear. Now, whatever I do to one side, I have to do to the other side. So I'm going to divide this by 720. And this is going to give us our final answer, right? Because now, look, we have H all alone. The 720s canceled each other out. So we just divide this number and we will get our answer, right? 8,000 divided by 720 is 11.1 repeating. Interesting. All right, let's go back to the Jamboard. So it's going to take a little more than, what this means is it's going to take a little bit more than 11 hours for this pump to finish pumping out the entire 10,000 gallon pool. Okay. 11.1 is our time. Now it's a repeating decimal. So it ended up being 11.11111111. Obviously, we know how to write that with the bar, right? We talked about that back in September. We write that with a bar for the sake of ease and clarity. All right, let's go to the video.
How long it would take to pump all the water into the tanker.
All right, so they got the same thing we got, right? And they did the same thing we did. I just wanted to show you and explain to you how we do this math, right? Because they do it real quick and they just go boom, 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 and it's way too fast for you to see what's going on. But they did the same thing I did, right? They had a plus 2,000, so they subtracted 2,000 to get rid of it, and they subtracted 2,000 to the left side because, again, whatever you do to one side, you have to do the exact same thing to the other side. You have to do the same thing to both sides when you are solving an equation for a unknown variable, for an unknown variable, right? In this case, our unknown variable is h. We need to find what h is, so we need to isolate it. We need to get it all alone. They did the exact same thing I did. Then they divided by 720, both sides, cancel that, divide that, and they got 11.1, right? It's 11.1 repeating. So it just goes on forever. They rounded off to 1 decimal, or 2 decimals. Sorry, I rounded off to 1 decimal. And you can see that they have this little squiggly eye, right? That means it's approximately equal to, because to be technically correct, they would need to write 11.1111111111, right? So they just rounded it off. So because it's close but not exact, they use the little squiggly guy. So some math books and some people will use the equal sign with the squiggly. I personally use this. It's like a squiggly equal sign, okay? Either one of these mean the same thing. They mean it's about equal to, it's approximately equal to, but it's not quite exact, right? That means it's pretty much dead on, but it's not quite exact, right? It's a wavy equal sign. That's what that means. Okay, let's go on.
Another way to solve the problem is to use the information given to make a graph. In this graph, the y-axis shows the water pumped in gallons, and the x-axis shows time in hours. Let's plot some data points.
Select your answer.
All right, so we are now going to make a graph for the scenario. What's the point that represents the initial value or the starting point? Well, if we think back to what we did, it said that there were already 2,000 gallons pumped, right? The scenario said there's already 2,000 gallons that have been pumped. So my starting point on this graph is going to be 2,000.
Your initial value is 2,000 gallons.
So again, because that was our y-intercept in our linear equation, that makes sense, right? That's going to be our first point. When you guys were doing your delta math homework, when you had to graph lines and it gave you y equals mx plus b, or one of them just gave you a slope and an intercept, you had to go to the intercept first and you graphed it, right? If the intercept was +3, you went up 3 spaces, boom, 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 and you put a point. You plotted a point, right? And then if the slope was 4/2, you went, that's a bad example. If it was 4/3, you would go up 1, 2, 3, 4, and over 1, 2, 3, right? So we know that the intercept is the starting point, and the intercept or starting point is 2,000.
You know that you can pump 720 gallons each hour. Now draw a line through the data points. The line has a slope of 720.
Right, that's hard to see because these, these are going by thousands. Each box is 1,000, right? This is 2,000, 3,000, 4,000, 5,000, 6,000, etc. So this went up 720 gallons when it went over 1 hour. As you can see, these go by ones, right? 1, 2, 3, 4, 5, 6, blah, blah, blah. So this went up 720 and over 1, up 720 over 1, up 720 over 1. That is our slope, which is our unit rate or our constant, right? all this stuff makes sense now. We're tying stuff together, tying things together that we've already learned into new concepts.
It's a straight line, so it's a linear function. The total water that needs to be pumped is 10,000 gallons. You could extend the line to find the value of x when y is 10,000. Now you know how to represent a linear function using a bar diagram, an equation, and a graph.
All right. So if we look at this, the answer we got was 11.111111, right? 11.1 repeating. If we look at this graph, when the water hits 10,000 gallons pumped, which is this line right here, it's right here, which is just a little bit more than 11. Would you look at that, right? This is 10, 11, 12. So right here is 11.11111111. So that graph with a slope of 720 and a y-intercept of 2000 exactly represents our scenario, right? A graph, and you can represent this, like they said, in a graph, in an equation, or in a bar diagram. Some people call them tape diagrams, right? All three of those are three different ways you can solve the problem. The best and easiest way is to probably use the equation, because you can get an exact figure, right? If you didn't know the equation and you just tried to look at this graph, you would be guessing. You know it's a little bit more than 11, but you're not sure exactly where it is, right? If you solve using the equation and you solve for, in this case, h, the unknown, you can find the exact value, right? But those are three different ways to do this problem. All right. Do I have any questions? How are we doing? How are we doing today? Is everybody doing okay? I am going to open it up. Anything here, or are you guys ready to go on? All right, give me 1 second here. Because, Skylar, thanks for joining us this morning. Good morning. Thanks for being here. I am actually going to start you on something else. I appreciate you being on. Last week we took the map test. So I'm actually going to start you on the map test, okay? Because we need to get those done. The time frame to get those done, and we only have like one or two more weeks to get them done.
I've
So
been sick for the last few days, and I just got the hospital last night, but I have to go back to the hospital tomorrow. So all the work that I've been missing from your class and stuff, can you just send it to me, and I'll just do it when I go back to the hospital?
yeah, I can do that. Do you check your CPS Gmail?
Because
Yeah,
I supposed to did a test in somebody else's class, but I had told them that I've been in the hospital. So Susie said she want me to make it up.
Yeah, that's fine. That's fine. Yeah, I'll send you all the work. All the work for me is on Delta Math this quarter.
Okay.
So I'll send you the link to Delta Math, and I'll send you your password and your username. Your username is just your, I don't know what it would be, but like kwalker@cincinnatips.org, and then your birthday, and then your, it's really easy.
I'm sorry I haven't been logging on, but I've just been in and out the hospital.
Oh, you're good. I mean, I know it's like this time of year is it's not this time of year, but this year, I should say, like people are getting sick. That's kind of the whole point of why we're at home, right? I'm at home. All the other teachers are in the building now, but I'm at home because I've been sick. I haven't been really sick. I'm obviously well enough that I can still be on the computer, but I've been home for the last few days because I've been sick. It is what it is. So I'll tell you what, I'm gonna start this session here. I'm gonna make sure you're in it. Because yeah, if you're gonna have to go back tomorrow, then I'm gonna get you started today, and hopefully we can get this knocked out. So let me put this in the chat for you, and then I will get back to the lesson. Actually, do you want to go on to a different meet so you don't hear us talking? Let me do this. I'm gonna start a new meet. I'll call it because I don't want you to have to be bothered by hearing us talk either. I just started a meet. It's called Levine Math. Why don't you go over to that, and then I will get you started on the test, okay? And then I'll get back to teaching and doing the lesson.
Okay.
Fellas, thanks for bearing with me here. Let me see. 4180. All right, so go. Yeah, all right, cool. You're on. Awesome. All right, I see you on. Okay, guys. Sorry about that. We'll get back to doing our equations here. Let's go to present a tab. And we'll go back to it. All right. We're back. So we just talked about this. Obviously, we're going to go to the next one here. We have a Desmos graph that we can manipulate here and change around. So this is going to be cool. It says, I think it's giving us the exact same information here, right? This is the exact same information we just had. 10,000 gallon swimming pool needs to be emptied. Exactly 2,000 gallons have already been pumped out. As the pump is pumping water, the amount of water in the pool decreases at a rate of 720 gallons per hour. It's exactly the same problem. It just wants us to graph the line, right? So it says which number represents the y-intercept and which number represents the slope. So we would have to type in the y, gosh darn it, y-intercept is 2,000. That is our starting point. Typing awfully today. I got a paper cut on my finger. It really hurts. So my right thumb is killing me. I can't type worth anything today, right? Here we go. All right, guys. Sorry, I was just helping Kayla get started on her test real quick. Let's go back to this. I was talking about my paper cut and my terrible struggles in typing. Right, our y-intercept is 2,000 because that was our starting point. Our slope is 720 because that is our unit rate. Right? Like that, so it stays in one line. So we need to graph this. Let's graph this first point. We need to go to about 2,000 here. This is 1,500. Well, let's see if I can manipulate this graph somehow. We need, it doesn't really have 2,000 labeled. Well, this is weird because the labels on this graph are kind of off. So this is 1,500 and this is 3,000. So we need to pick where 2,000 is going to be. Well, halfway, if this is going by 500s, this would be 2,000, 2,500, 3,000. So it's not going by 500s. It's not going by thousands, obviously, because that would be 25, 35, 45. It looks like it's going by, I don't know, maybe roughly 400s. But we're going to estimate this. I'm going to put it right here. We'll just estimate it for now. We'll call that 2,000. We don't know exactly where it is because I don't know why they labeled the graph like this, but it is what it is. Okay. So now our slope is up 720 for over 1. So they have labeled the time in 10 hours. Okay. So if we go up 720 for over 1, then we are going to go up 7,200 for over 10, right? Because if you just multiply both those numbers by 10, right? 1 times 10 is 10. 720 times 10 is 7,200. So let's go up 7,200. We had to add our initial 2,000 plus 7,200 is going to be 9,200, which will be somewhere right about here. So on 10, we should be right about there, right? Now, I know this one, I don't know why they labeled this graph the way they did. So this may be confusing to you, and that's okay. It was confusing to me. Now, they should have just labeled this graph by thousands to make it easy for us, but they didn't. So whatever. They wanted to be difficult today. But that's how we would graph that, right? Our starting point was 2,000. That was our intercept. So we graphed that as 2,000 on the y-intercept. And then our slope was 720. So we went up 720 over 1, up 720 over 1, up 720 over 1, up 720 over 1, blah, 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 blah. We did that 10 times to get here, right? So that's an approximation of what we got. How is the rate of change of this function different from that in example 1? It's not. It's not different at all. As the pump is pumping water, the amount of water in the pool decreases at a constant rate of 720 gallons per hour. It's the exact same. So I don't know why they even asked us this. It's exactly the same. So let's just go on because I'm done with this problem. This problem was poorly written and the graph was confusing. Let's go on to a different one and try another one. All right. How can you determine whether the relationship between side length and area is a function? All right, we talked about functions starting yesterday, right? How can we determine whether the relationship between side length and area is a function? Now remember, the characteristic of a function is for each input, there is only one output, right? That was what we talked about on Tuesday. For each input, there can only be one output. If you have two different outputs for the same input, you do not have a function. And that is going to be on your Savas homework this evening or this afternoon. It's going to post, I don't know, sometime this morning. I think I said to post at like 10 a.m. So you guys can even do it during study skills if you want. But let's look at this graph.
Little baby,
Yeah, what's
I ain't
up?
gonna lie. I've been asleep this whole time.
All right. Well,
So basically, is this the stuff we did yesterday?
this is the stuff we did Tuesday. Yeah, this is the stuff we did Tuesday. So I was just kind of reviewing that. To make something a function, or for something to be a function, for every input, which is usually this left column, right? The x column. If we do a t-chart, it's always x and y. Just like if we plot points, it's always x comma y. For each input, there can only be one output. So if we look at this, 0, we get 0, 1, we get 1, 2, 4, 3, 9, 4, 16, 5, 25. We look like we have a function here, right? Because there are no duplicate outputs for the same input. If we had 1, 1, and then 3, 1, 3 was 1, now we have, oh, I'm sorry, I had that backwards. If we had 1, 1, and then a 1, 4, we would not have a function, right? Because we would have two different outputs for the same input. But for this one, we have 6 different inputs, and they all have their own unique outputs, right? There are no duplicates. So we have a function, right? So we can say that the side length and area are a function. The area of the square is a function of side length, which is true, right? The longer the side length of a square, the bigger the area will be. That is true. All right, let's go to the next slide and see what they do here. All right, so it's going to ask us to plot the points here. All right, so when the side length is 0, the area is obviously 0, because if you have a side length of 0, you don't have a shape, you have nothing, right? So now it's plotting these points, right? It graphed them. When the side length is 1, obviously in a square, all sides are the same. So the area is length times width, right? Area is length times width. So if it's 1, it's 1 times 1, which is 1. So when the side length is 1, the area is 1. When the side length is 2, the area is 4. That's here, right? Because 2 times 2 is 4. When the side length is 3, you have 3 times 3, which is 9. Right? So they plotted that one right here. 4 is 16. 4 and 16, right? And 5 is 25. Here's 5, and then up to 25. So you can see that this is growing. We call this exponentially. This is not growing in a linear manner. This is growing exponentially. Okay? It is a curve that is going up. And the bigger we make the size of the side, the more rapidly the area will grow. If we extend this out to 10 times 10 is 100. So let's zoom out a little bit and see if we can. Oh, it's not going to work. It's not going to work. That's okay. It's not going to zoom out for me. But you can see that this curve is going to continue to grow exponentially. It's not growing at a constant rate. A constant rate would be a straight line. This one, the bigger the side length, the more rapidly the area will grow, right? It's not growing at a constant rate because we are multiplying something. We are multiplying something times itself, right? So what they're trying to get at here is the graph of this function is not a straight line, so it is a non-linear function, okay? Linear means line. It should be kind of self-explanatory, but that's what it means. Linear means line. It has line in the word, right? Linear, line. A non-linear function is a function that has a curve in it, okay? It is not a straight line. And obviously we know that if it is not a straight line, we do not have a constant rate, right? We have a rate that is changing, right? You know that to have a proportional relationship, we have to have a constant rate, a straight line, and we have to have the point start at the origin, right? So back in like October, we were talking about what makes a graph of a proportional relationship. This one starts at the origin, 0, 0, but it is not a straight line. It is a curve. So we do not have a proportional relationship here. We do have a function, right? Because we already showed that this passes the function test. For each input, there is only one output. There are no duplicate outputs for the same input here. So, all right, let's go on. Is everybody with me that this is a nonlinear function? A nonlinear function because it's not a straight line, right? That's what that term means. So that is an important takeaway from what they're showing you here. Nonlinear means it's not a straight line. Linear means it is a straight line, a perfectly straight, could be diagonal, could be straight across, could be whatever, but a linear function is a straight line, right? Okay. Let's go to example 3. All right. Determine whether each line represents a function. This is getting at something new. I am going to tell you guys something new. When you look at graphs, there is a way to determine whether or not the graph is a function. I'm going to write it on the Jamboard. It is called the vertical line test. The vertical line test can help you determine whether or not something is a function. Now, this is on page 173 of your textbook. So this exact page, these exact graphs right here are on page 173. So you can actually do these and you can actually perform the vertical line test on these 3 graphs to see if they are a function or not. Now, the way the vertical line test works is if we have a graph, let's try to replicate what it's doing here. We have a graph that looks kind of like this, right? That's kind of what our graph looks like. If I draw a vertical line, which is straight up and down, anywhere on this function, does it cross in more than one place? No. So it is a function, right? If a vertical line at any given point does not cross at more than one place on this original line, then it passes the vertical line test and it is a function, right? So let's do another one here. Let's do this one, which kind of looks like this. And then the last one looks like this. All right. The vertical line test. Again, we can draw completely vertical, straight up and down lines here. And anywhere we draw a vertical line, that vertical line only crosses at one place. It only crosses this function at one place. So what we have is we have a function, right? It passes the vertical line test. So we have a function. Excuse me.
What?
We have this one as a function, right? Because it passes the vertical line test. We drew a bunch of vertical lines and they only cross at one place. Now, let's look at this third one. If we start drawing vertical lines, what happens? This crosses at 2 different places. These vertical lines are crossing at 2 different places on the graph. So this fails the vertical line test. So this is not a function, right? Does everybody kind of get what I'm getting at here at the vertical line test? If you see a graph and they ask you, is this graph a function? You can use the vertical line test to determine whether or not it is a function. And the reason the vertical line test works is if we think back to our original definition of a function cannot have more than one output for the same input, right? If I input the number 1, I can only get one output, right? Well, let's say this is 1 right here. 1, 2, 3. If I input the number 1, I get 2 different outputs. I get -2 and I get 5, right? So for one output, for one input, I got 2 different outputs. That's why it's not a function. And that's why the vertical line test works. Right? For this one, if I input 1, I get -5. And that's the only result I get. I get -5, right? There's no other at 1. There's nothing up here that's along the 1 line, right? So the vertical line test is a way of testing a graph to see whether there are more than one output for the same input, right? If you fail the vertical line test, if the vertical line crosses at 2 different places, you don't have a function. All right, let's go back to the Savas. The graph represents a function because each x value corresponds to exactly one y value, right? And that's what we were saying. This, if we started doing the vertical line test here, and you can even almost use the grid lines, like see the vertical grid lines? You can use all these vertical grid lines as vertical line tests. They only cross at one place along this line, right? Same here. They only cross at one place along this line. It's a curvy line. So we have a nonlinear function, right? This is nonlinear. It's got a curve, but it is a function, okay? This right here is not a function because there are more than one value for the same input. Again, if I input 1, I get 1 is 0, and 1 is also 6 or 7. I can't tell. 6. If I input 1, I get 0 and 6. If I input -2, I get 1 and I get 5. I get 2 different values for the same input. So this is not a function. All right. And you can see, like, if I use this vertical line right here, it crosses at 2 different places. Right? So you do not have a function. This one right here, obviously we said it was a function, and this one right here is not a function. So again, think about the vertical line test. If they say, if a question asks you, look at this function on a graph and tell me whether it's a function or not, use the vertical line test, right? If the vertical lines are only crossing at one place along the function, it's a function. If they cross at more than one, sometimes you could have them that cross 3 or 4 times. Usually you don't. But if it crosses more than one time when you draw a vertical line through the function, at any point in the function, if a line can touch 2 different places on the graph, you do not have a function. It fails the vertical line test, right? All right. Draw a graph.
Draw a graph.
I don't need you to tell me. Draw a graph that represents a linear function. What equation represents the function? So they want us to draw a graph and then make an equation for it. Okay. So get off that. There we go. Let's use red so it stands out. All right. So they want us to draw a graph of a linear function. Why don't we do, let's do this. That's a linear function, right? It's a straight line. It has no bends and no curves, no dips. It's a straight line. We've drawn a linear function. Now it wants us to draw an equation to represent this. So what I'm going to do is label some points here. My y-intercept is right here. That is 1, right? It's one space up. One space. So my y-intercept is going to be +1. Now let's figure out what my slope is.
My bad.
You're good. I heard you. I heard your message ding. You're good. Let's find out what our slope is here. If I start right here, I'm going up and then right? Rise over run. So the rise is 1, 2. And the run is, I'll use purple. 1, 2, 3. So the rise, well, we can just do this. The run is 3. The rise is 2, right? Everybody see how that works? And then obviously we're going to have an x here because the slope is attached to the x. So we have y equals mx plus b, where our slope is there and our intercept is there, right? Our slope is rise over run, right? So we have up 2, we're right here, up 2, and over 3, up 2, right 3. That's our slope, 2 and then 3. And our starting point was +1. So we started right there because we went up one space. We see 0, and then we went up one space to get to our starting point. That's what the +1 means. So that's some review from last chapter. All right. Y equals 2/3 x plus 1. We drew a line and then we wrote a function to model it. Okay. We good on that? Any questions? What you got?
Can you do another one?
Yeah, let me clear this out and we'll do another one. I wish I could let you guys like write on my screen, but I don't have the capability to do that, unfortunately, because I would let you guys try it and see what you get. But let me just hit the delete button and let's draw another one. I will use red again to represent our line. All right, I'll get you guys to do some input here though. What should we make our y-intercept? What should our starting point be? Give me a number, a positive number or a negative number, doesn't matter.
-5.
-5, okay. So let's go plot that point. -5, 1, 2, 3, 4, 5. Okay. So our intercept is going to be right here. Okay, that is -5. So now what should our slope be? Give me a slope. Rise over run.
Positive 10.
Positive 10. So we're going to go up 10 and over 1. Okay, we can do that. Well, let's go up 10. So our slope is 10 over 1 x. And then our intercept is going to be -5, right? That's what we're doing here. So our slope is 10. So let's go up 10. Whoops. 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, now I'm off. What did I do wrong? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I went up 10 and over 1.
What is that?
Wait, but why did you go left instead of right?
I was just counting the spaces. I went right. You see my green? I did go right at the end. I was just doing these to count the spaces to show you that I counted 10. It doesn't matter if you draw them over here. That was just for illustrative purposes only, okay? Really, this doesn't matter, right? I was just counting my 10 spaces, and then I counted my 1 space to the right. Because you're right, you are correct that we always go right when we're doing slope, right? If it's positive, we go up. And since it's positive, right, we went up 10, and then we have 1. So we went over to the right 1 space. All right. So then we have to plot our second point, which goes right there. And now we have to connect the dots. Oh, my line's going to be awful. I'm doing the best I can. But are we good? Does that look like it's correct? My line is terrible because I can't draw a straight line to save my life. But according to the function we have, according to this equation that we just made up, this equation does represent this line, right? We started at -5. That was our intercept. So we plotted that point. And then we said the slope was +10. So we went up 10 and right 1. Up 10 and right 1 to get to this second point right here. And then we just connected the dots. So how we feel about that? I know we wanted to do another one. Does that kind of solidify what we're doing here? Does that kind of refresh your memory? All right, I think we got one more example here. Yep. So let's do one more example here, and then I'll let you guys go and you can work on some delta math. Okay, this one's, we've already kind of done one. Let's skip that because that's the same. It's the same question with different numbers, right? It's a pool. This one says 14,000, 2,800 have already been pumped, and it's a different unit rate, but it's the same question. So that's a little boring. Let's go to this additional example 3. The graph shown represents a function. The tiles list the other points that could be added to the graph. Which of the following points can you add to the graph so that it still represents a function? Okay, so remember, we can't have a duplicate output for the same input. If I put in x is 1, I can only have 1 point on the x is 1. Okay, so let's look at this. 2, -1. At 2, -1, it's x comma y. So if I go to x is 2, y is -1, I would have to put another point right here. Well, that would be 2 outputs for the same input, right? Because 2 is already 2. So 2 can't be -1. So that would be not a function. Let's look at -3, 0. -3. Well, there's already a -3 here at -3, right? So if I put another point here at -3, 0, we would have 2 outputs for the same input. So that does not work either. Not a function. -1, 4. -1 up 4. Well, we don't have any other -1s yet. So -1, 4 can still be a function. Now, this is obviously not going to be a linear function. It's going to be a zigzag, right? Boom, 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 boom. It's a zigzag line, but it's still a function because for each input, we have only one output. 0, -3 also could be 1 because we don't have anything at 0 yet. Again, it's x comma y, so 0, -3, 0, and then we go down 1, 2, 3. We would plot a point. That could work. Okay, just because it's a zigzaggy thing or a curvy thing doesn't mean it's not a function. It's just a non-linear function. Again, it's all about the vertical line test, right? If you're looking at a graph, does it pass the vertical line test, right? Does the vertical line you draw only cross at one point on the line? Let's go to the next one here and let's see what's up. Okay. Again, not a function, right? Because there are 2 outputs. Not a function. If we had this as an output, this would not be a function because there are 2 here. These are also the same, right? -1, -3, and -1, 4. So we would have to pick one of these and get rid of the other one if we wanted this to still be a function. So if we plot all 4 of those points, then technically none of them would work to make this a function. We could make it work if we picked one or the other of these, right? This is a little, the way they graph this and explain this is a little confusing, but hopefully the vertical line test really helped you guys understand what's going on here. Okay, like if I have a function, and I'll go back to this and share my screen from when I was drawing, right? We draw these vertical lines, and just remember, when we start drawing vertical lines on this graph, if the vertical lines only cross at one place, it passes the vertical line test. It's a function, right? All of these vertical lines only cross at one place along these functions. So we have a function. This one, if we draw a vertical line here, it crosses at 2 different places. So it's not a function. It fails the line test. All right, guys, I'm going to let you go a few minutes early here. We wrapped up what we needed to do. So I appreciate you guys being on. I'm going to stop the recording. I'm going to open it up for any questions, or you could use these 10 minutes to do a couple Delta Math problems. It's totally up to you. Let me stop our recording here so I can upload it for those of you that are going to watch this at home. Why are you not? Man, this thing is. Here we go. Okay. All right, we're done. If you have any questions, now's the time.